Gravity is one of the four fundamental forces of nature, alongside electromagnetism, the strong nuclear force, and the weak nuclear force. It is the force that causes objects with mass to be attracted to one another. This force has been studied for centuries, and it is still not completely understood. However, there have been many attempts to visualize the nature of gravity, and some of these attempts have led to groundbreaking discoveries and insights. One of the earliest attempts to visualize gravity was made by Sir Isaac Newton. In the late 1600s, Newton developed his famous theory of gravity, which stated that every object in the universe attracts every other object with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This means that the force of gravity between two objects increases as their masses increase, and decreases as the distance between them increases. To visualize this theory, Newton developed a thought experiment involving a cannon on top of a tall mountain. If the cannon were fired with enough force, the cannonball would travel in a straight line and eventually fall to the ground due to gravity. However, if the cannon were fired with enough force, the cannonball would travel so fast that it would travel all the way around the Earth and return to the cannon. This thought experiment helped to illustrate the concept of orbital motion, and it was later used by the Russian physicist Konstantin Tsiolkovsky to develop the first mathematical model of spaceflight. Another attempt to visualize gravity was made by Albert Einstein in the early 1900s. Einstein developed his theory of general relativity, which stated that gravity is not a force that is transmitted between objects, but rather a curvature of spacetime caused by the presence of mass and energy. In other words, objects with mass distort the fabric of spacetime around them, causing other objects to move in a curved path around them. To visualize this theory, Einstein developed a series of thought experiments involving elevators and falling objects. He imagined an elevator in freefall, and observed that objects within the elevator would appear to float in mid-air, as if there were no gravity present. This led him to conclude that gravity is not a force that pulls objects down, but rather a curvature of spacetime that causes objects to move in a curved path. Einstein's theory of general relativity has been confirmed by numerous experiments, and it is now considered one of the most accurate descriptions of gravity. In recent years, scientists have continued to develop new ways to visualize gravity. One of the most exciting developments has been the detection of gravitational waves, which are ripples in spacetime caused by the collision of massive objects like black holes and neutron stars. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time, confirming a prediction made by Einstein a century earlier. To visualize these waves, scientists have developed computer simulations that show how spacetime is distorted by the collision of massive objects. These simulations show how gravitational waves propagate through the universe, and they provide valuable insights into the nature of gravity and the behavior of massive objects. Another recent development in the visualization of gravity has been the use of virtual reality technology. In 2018, researchers at the University of Portsmouth in the UK developed a virtual reality simulation that allows users to experience what it would be like to fall into a black hole. The simulation uses data from computer models of black holes to create a 3D environment that simulates the experience of falling into a black hole. Overall, the visualization of gravity has played an important role in our understanding of this fundamental force. From Newton's cannonball thought experiment to Einstein's elevator thought experiment to the detection of gravitational waves, these visualizations have helped us to develop new theories and unfortunately, we don't have any direct quotes from Newton or Einstein specifically regarding gravity visualized, as this term was likely not used during their time. However, we can make some educated guesses based on their work and writings. Sir Isaac Newton was known for his use of thought experiments to help visualize and understand the behavior of gravity. For example, in his famous Principia Mathematica, he used a thought experiment involving a cannon on a tall mountain to illustrate the concept of orbital motion. He also used the example of an apple falling from a tree to help explain the nature of gravity. Newton believed that by using these visualizations, people could better understand the laws of physics and the behavior of the universe. Albert Einstein, on the other hand, developed a more abstract understanding of gravity through his theory of general relativity. Rather than viewing gravity as a force between objects, he saw it as a curvature of spacetime caused by the presence of mass and energy. While he didn't rely as heavily on thought experiments as Newton did, Einstein did use them to help explain his theories to others. For example, he used the example of an elevator in free fall to help visualize the concept of weightlessness and the equivalence principle. Overall, both Newton and Einstein recognized the importance of visualization in understanding the behavior of gravity. While their approaches were different, they both understood the value of using concrete examples and thought experiments to help people understand complex scientific concepts. Sir Isaac Newton's Principia Mathematica is widely regarded as one of the most important works in the history of science. In this book, Newton laid out his 3 laws of motion and his law of universal gravitation, which described the behavior of gravity and its effects on objects in the universe. Here are some of the key contributions of Principia Mathematica to our understanding of gravity. Universal gravitation. Newton's law of universal gravitation stated that every object in the universe attracts every other object with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This law provided a mathematical framework for understanding the behavior of gravity, and it allowed scientists to make accurate predictions about the motion of planets, moons, and other celestial bodies. Kepler's laws. Newton used his law of gravitation to derive Kepler's laws of planetary motion, which describe how planets move in elliptical orbits around the Sun. These laws were based on the observations of the astronomer Johannes Kepler, and they provided a quantitative explanation for the behavior of the planets. Newtonian mechanics. Newton's laws of motion, which were also presented in Principia Mathematica, provided a foundation for the study of mechanics and the behavior of objects in motion. These laws allowed scientists to understand the behavior of objects under the influence of gravity and other forces. Experimental verification. Newton's theories of gravity and motion were supported by a wealth of experimental evidence, including the observations of astronomers and the results of laboratory experiments. This evidence helped to confirm the validity of Newton's theories and provided a basis for further research in physics and astronomy. Overall, Principia Mathematica provided a comprehensive and rigorous framework for understanding the behavior of gravity and its effects on the universe. Newton's contributions to the field of physics have had a profound impact on our understanding of the natural world, and his work remains an important foundation for modern physics and astronomy. As technology and scientific understanding continue to advance, it is likely that we will be able to visualize and understand gravity even better in the future. Here are a few reasons why. New observational techniques. Scientists are constantly developing new techniques for observing the universe, such as gravitational wave detectors and high-resolution telescopes. These tools allow us to see the effects of gravity on a variety of scales, from the behavior of black holes to the formation of galaxies. Improved computer simulations. With the increasing power of computers, scientists are able to run more complex simulations of gravitational interactions. These simulations allow us to visualize the behavior of gravity in a variety of scenarios, from the formation of planets to the collision of galaxies. Advancements in fundamental physics. The study of fundamental physics, such as quantum mechanics and string theory, may lead to new insights into the nature of gravity and its interactions with other fundamental forces. These insights could lead to new ways of visualizing and understanding the behavior of gravity. Interdisciplinary collaborations. Collaboration between physicists, mathematicians, computer scientists, and other researchers can lead to new ways of visualizing and understanding the behavior of gravity. For example, the development of new visualization techniques in computer science can be applied to the study of gravitational interactions. Overall, it is likely that our understanding of gravity and our ability to visualize it will continue to improve in the future. As we uncover new insights into the nature of the universe and develop new tools for observation and simulation, we will be able to better understand the behavior of gravity and its effects on the universe.